So welcome everyone to the seventh talk on Soergel bimodules. As I said, take everything today with a pinch of salt because this is kind of an improvised talk. And my goal today is to push the diagrammatics a little bit further, which we have seen last time. And the goal for today is to present you what I call the one color Soergel calculus, which is basically the main meat for the general Soergel calculus, which will be a diagrammatic description of the category of Soergel bimodules. So what do I mean by one color? Let me just tell you that because well, next time we will have two color, and then we will have the three color. Two color. And the point here is, so what does this mean? Well, remember that we have W, our Coxeter group, so there was some associated Coxeter graph, whatever it is, something like that, whatever, something like that. And I want to think of, and that's how the Soergel calculus will work, I want to think of the vertices, so the simple reflections, as being colors. Okay? These guys are colors. So the one color calculus means, the one color calculus is just have one simple reflection, and two color would be something like this. And the really surprising fact, which we'll see, I think in 2 weeks or so, is that this is basically sufficient to describe the whole Soergel calculus. A priori, you would guess that there might be relations involving whatever 500 simple reflections, but they're not. The worst case we see is actually the three color. So the worst case is, which you will see, is three colors. But these are not really important. Well, they're of course important, but they don't turn up in practice usually. So I kind of want to ignore them, at least for today, at least for next week. And I'd like to stress it again. I mean, this is very surprising. You're kind of categorizing a Coxeter group. In principle, I have no idea what to expect. There could be relations involving 500 simple reflections, as I said, but it turns out there are no relations involving 500 simple reflection, or to be precise, you can always break them down into relations with one color, two colors, or at most three colors. And the three color ones they really don't turn up in practice. Okay, so the goal is to explain how the diagrammatics from last week actually carries over to Soergel land. Very good. So let me do a recap for you. So what we have seen last time in our talk. So recap diagrams for two categories. And how does this work? Well, in the two category, so let me do a two category here. And I will switch in a second to monoidal category, so let me just do it here, which are a little bit easier, special case. And in the two category of objects, whatever, ABC, we have morphisms, whatever, FG, we have two morphisms, alpha, beta, something like that. And in the monoidal category, you kind of cut it off here. So in the monoidal categories, is the two categories with one object. And whenever you have just one object, like a fixed point, you usually tend to ignore it. So you basically have no notation for this object. And then becomes something weird, which takes a while to get used to it. But people in this setup call now the morphisms in the 2 category actually the objects of the monoidal category. So please don't get confused. And the morphisms are then as 2 morphisms are then called morphisms. And the point is the whole diagrammatic. So this is just a convention. So whenever I talk about objects or morphisms in monoidal categories, they are actually morphisms and 2 morphisms in the 2 category. This is just really bad terminology. I don't know who to blame it on, but well, we have to deal with it. So we get used to it. So very good. And now the diagram calculus works as follows. So the objects here become actually faces, which are 2 cells, right? 2-dimensional objects. The morphisms here become lines, so 1 cells, 1-dimensional objects. And the 2 morphisms become, well, points, so 0 cells, 0-dimensional objects. And the same is true on this side, just that this is just nothing, and you only see lines and points. Okay, here's an example. So on this side, we might have something like this. So here you have faces labeled by some object, whatever it is, A, B, C, D. You would have lines labeled by morphisms F and G, and you would have points labeled by 2 morphisms like alpha. And on the other side, the picture gets a little bit easier. It's basically the same, but now I ignore the coloring of the faces because I only have 1 object to begin with. So something like that would be a picture in a monoidal category. And I'm going to use these for basically the rest of the talk. Okay, let me summarize this slide because I need to make a new one. We have seen last time in Anna's talk this diagrammatics, and it turned out to be very useful because you basically have topological relations that those diagrams satisfy. And the easy thing I want to do is this part here, which are usually called string diagrams. Well, why are they called string diagrams? Because they look like those pictures, like strings. Very good. So let me start with something where you already can see really the power of diagrammatics. I want to start with the following very classical notion of an algebra. Okay? But I want to do it a little bit more general. I want to talk about an algebra in a monoidal category. So let's see. And C always means I have tensor product and a monoidal unit, a monoidal category. And everything, I just write strict. It doesn't really matter, but I want strict category. So strict is just terminology that I don't have to worry about stupid associators. And in algebra, A in C is an object. I write A in C just for an object. Is an object. A, and I really should write, but I won't do it. I should write it's a triple. It's an A, it's a mu, and it's a iota. So my last symbol is supposed to be a iota. Is an object A together with two morphisms. mu from A tensor A to A, and iota from the endomorphism in C. Sorry, this was too quick, just from the monoid unit to A. Such that something holds, okay? And I will write it down, and then I will write pictures, such that the following holds. All right, I will give you an example in a second, but basically what I'm trying to do right now is I'm trying to generalize the notion of an algebra. So certainly I want something like unitality of a unital algebra, so something like unitality and associativity. And if you think about it a little bit in terms of categorical diagrams, it would be the following. So such that associativity holds, and that's the following commutative diagram. A, right? You have, so usually we would write something like A, B, C equals A, B, C, but I don't know what elements are in the category, so let me try to write this in a diagram. So what can I do? Well, look at this equation. Let me put this one here, and let me put this one here. This is just saying I first multiply, so this one here is just saying I first multiply and B and C, and then I multiply with A. So I'm taking identity, tensor my multiplication, and then I multiply, right? And here's the other way around. I take multiplication on the first two factors, and then identity, and then I multiply. And this should commute. So this commutes. And then you, well, so this is just associativity in terms of diagrams. And then you have also unitality. Whenever you have something like A times, it should be A, it should be A times 1. Again, this is bad because I don't know what elements are. So let me phrase everything in terms of a commuting diagram. So this is just equal. All right, and let me see. I want to put this one here and this one here. So to make it a little bit nicer, I add my trivial object here. Of course, trivial object times A is just A. And what I could do here is I could first apply this was supposed to be iota and then identity, and then I multiply. Right? That's exactly what's going on here. Or I could do the other way around. Oops, sorry. I can first use iota. Oops. Okay. Could do that. Let me give you an example, and then let's do the diagrammatic calculus. Let's go back. So we have two commuting diagrams, which essentially mimic the definition of an algebra that you're used to. And indeed, maybe if you want an example. So an algebra is, in this setup, is an algebra and the choice of a parent category. So an algebra, for example, a vector would be an algebra in the usual sense. And I've just written down an element-free definition of what it means to be an algebra. Okay, specifically, for instance, I've used this example several times. For example, here's a very small algebra which I really like. So it's a polynomial ring, and I just kill everything, all polynomials of degree 2. As a vector space, this is just had just 2 basis elements, and the multiplication is what you think it is, just killing everything which is of degree 2. With, well, mu and I would write it like this. And u is just sorry. Just what you think it is, and iota, I still have some space here. And iota, upsala. What is the monoidal unit in vector spaces? It's my ground field, let's call it K. Oh, my ground field is C. Let's call my ground field C. Okay. Very good. So I have 2 natural maps. Okay, so far so good. Nothing really happened on this slide. Just a reminder what an algebra is, basically, and why all of these generalizes the algebra, the notion of an algebra. And I say it again, it's a kind of point-free definition of an algebra. And now you can plot in your favorite monoidal category, and you can study algebras in your favorite monoidal category, and they behave basically in the same way as classical algebras do. But I don't like this. The point is now I don't like those commuting diagrams. It took me way too long to write down. So let me do diagrammatics. Okay, diagrammatics. And I'll show you 2 versions. A short one, which we will usually use, and a topological one, which hopefully makes clear why all the relations are pretty natural. So I have 2 maps which I need to encode, the multiplication and the unit. So mu in diagrammatics would just look like this, right? Everything is labeled by A, and then there will be a one-dimensional thing named mu. And I'm just very tired. I'm just writing this thing. Right? I have an element. You should think about it like I have an element A and I have an element B, and they kind of merge together, and I get an element A times B. Very good. My alternative. So this is called the spine notation. You will see in a second why. So here will come an alternative, which I give you in a second. But let me just do iota. Iota will look like this. It goes from the trivial, which, as we learned, is always empty. I don't draw anything. Then there will be some label iota, and then I'm going to A. And again, I'm really tired, and I don't want to write always the stupid label, so I'm just writing kind of a reverse lollipop, right? It's a reverse lollipop. Or a dot, whatever you want to call it. Because again, spine notation. And why do I call it spine notation? Well, because it's kind of the spine of the following picture. I have 2 circles. There's another circle. And I can think of those circles as moving in time. So here are they moving in time. And I need to go to one circle. So at one point, those circles will collapse. And what you get is a pair of pens. So these are really, so this is, by the way, here's the spine, of course, of this pair of pens. And this is really a pair of pens, so it's hollow, right? It's a pair of pens. I could put it on. In principle, it's written on a tablet, but in principle, I could put it on. And the same here, this guy goes from nothing to a circle. And what can I do going from nothing to a circle? Well, I can do a cup. And it's again hollow. I can put water inside. And here is my spine. Okay, and now the relations are as follows. Associativity now looks as follows. And unitality looks as follows. In spine notation. And well, maybe that doesn't look quite topological because you're doing something singular. You're removing edges from a graph, for instance. But actually, let me draw the topological picture. This is a spine notation, and this is a topological notation. Let me draw the topological picture. What's going on? I have three circles. Need a little bit more space. There you go. And I want to go to one circle. And it should be equal to three circles going to one circle. Oops. And, well, it looks like this. Right? It's just, you can see the spine here. And this is really, I mean, it's just a height loop, right? It's just this one. This relation, so associativity, the classical associativity of algebras is actually a topological relation. When I first learned this, I was really stunned. I really like this. This is really good. The same here, unitality is also a topological notation. So let me do it. So what's going on here? It looks a little bit like this. So here is my little cup that I had, and of course this is just a cylinder, right? And the other side looks exactly the same. And here's again the spine. This is boring. Wow, this is a bad drawing. Let me try again. Okay, so upshot with a little bit more space. The classical associativity and unitality are actually topological notions. Okay, and if you don't believe me that it's an upshot, here comes the. So let me go back. So, right, this is a drawing, either in spine notation, and usually I will use spine notation. Today I stick a little bit with the topological notation. The only reason to use the spine notation is, of course, it's simpler to draw. I could draw all those pair of pens all the time, but it gets a bit tiresome. With the equivalent, let me give you an application. Which is absolutely immediate. So the proof is absolutely immediate. So application, well, lemma. Oh, I'm sorry. So let me just phrase it like this. Okay, what do I mean by that? Well, let's assume we're having first linear algebra class or whatever, and you see the notion of a group, you usually would see something like this. Some associativity. A, B, C equals C, B, A. Sorry, A, B, C. And that's what people usually call a definition. Well, this is part of the definition of a group. But actually, that's a horrible definition. But what you really, really want is that all bracketings are the same. So for instance, you would like to have A, B, C, D equals whatever way of bracketing it. And it's kind of a well-known proposition that the first one implies the second one, much stronger statement, which, by the way, as I said again, should be the correct definition of a group. The correct definition of a group or an algebra should be all bracketings are the same. But it's kind of nicely well known that the first one implies the second one. I don't say this proof using algebra is hard. You can do it yourself. But it's kind of a bookkeeping exercise. And I don't know how you feel. I don't like bookkeeping exercises. The same proof, so this implies the same proof in diagrammatics is basically trivial. So what do I have to observe is just the following. If I draw something with a certain number of circles here and something on the top, and I do anything crazy in between, whatever it is. Whatever it is, this is always just, let me give this name, so 1, 2, 3, 4, 5. This is always just an n plus 1 in this case. Function sphere. So, which immediately implies that no matter how you draw those associativity diagrams, they're all the same. Let me just call this real associativity, meaning that really all bracketings are the same, not just like 3 bracketings. And this proof works again for any monomial category immediately, not just for vector spaces or for groups or whatever. And this kind of the power of diagrammatics, right? It's just a topological argument. Whatever you do, you don't add a genus to it, so it has to be just a sphere. No matter how you write your lex, it doesn't matter. Very good. So an algebra, that was the notion of an algebra. And if you just look at those pictures, right? So this is algebra. Well, and you can, what prefers in this case bottom before top? Remember that actually I should draw a line here, and this is actually a morphism from bottom to top. Oops, this was the wrong one. I certainly have a preferred direction in those pictures. So the co-algebra is exactly the same. The co-algebra is a dual. I would draw a co-multiplication and a co-unit, and I recall the delta is a co-multiplication. And the co-unit I would write like this, like a real lollipop, not like a lollipop on its head. This is usually epsilon, a co-unit. And of course they have exactly the same pictures, just reversed. This one. And the corresponding relations that you think they should satisfy is exactly what you think it is. It's a long leg, short leg. Which one is short now? This one is short, this one is long. So this would be co-associativity. And co-unitality, well, let me do it like this. Co-unitality would look like this. You want something to be a cylinder, and what could it be? Well, you co-multiply first, put a cup. Something like this. And again, of course, you can draw the spines. Very good. So a co-algebra in a monoidal category is then completely defined the same way as an algebra in a category, just everything turned around. And this topologically absolutely makes sense. Why should bottom be better than top, right? Why should I prefer one side? And I personally think the only reason why people like algebras more than co-algebras is because we are usually earlier exposed to the notion of co-algebras. It's completely biased. But a priori, there is actually no reason to like one more than the other. It's just turning pictures. Let me give you an example anyway. So come back to my example. Oops. Well, you probably wouldn't be very surprised if I tell you now that co-algebras, in fact, are co-algebras in the classical sense that you could look up in any book from the 60s or whatever. So co-algebras, in fact, are just co-algebras, just classical co-algebras. For example, my friend here is actually a co-algebra with my two structure maps being the following: delta. Remember, I have just two objects. I have I only need to specify it on my two vectors. One is sent to remember that this guy has to go from, well, let me just write from A tensor A. From A to A tensor A. Right, I should start with one object and I should give you a tensor. That's exactly what this map does. And epsilon should go from A to the unit, which is just the ground field in this case. So I should tell you what epsilon does to those two objects, and it's the following map. There you go. So it just kills the unit and sends x to 1. And now you could check all those conditions that you would like to see satisfy those two. Okay, so algebras and co-algebras are, their relations are actually completely topological in nature. It's like playing with surfaces. But something is missing, okay? And here comes the key inside, which is, well, key inside, key question. In some sense, my topological diagrams are those surface diagrams. So actually, do those algebras and co-algebras already describe all relations you can cook up for surfaces? And the answer is almost, which is a pretty nice answer. Let me tell you. Key question: do we have all relations using just co-algebras? All, let me call them topological relations. You certainly need to use both, right? Because that was kind of a preferred direction. But do you need anything more? And the answer is we need one more relation, just one more. And then we'll draw it in a second. And the relation looks as follows. First, in spine diagrams, and then you will see in spine diagrams it looks a little bit strange, but in topological pictures it's pretty obvious. In spine diagrams it looks like this. If you first multiply and then co-multiply, that is actually the same as if you do this picture. So you co-multiply and do nothing, and then you multiply and do nothing. Looks a little bit strange. On the other side, you just do it the other way around. So that's called the Frobenius relation. Let me draw the picture for you to convince you that this is a completely topological, completely topological relation. So first, this is the middle picture. This is really just a 4 times function sphere arranged in a funny way. So basically what I'm saying is always to arrange a 4 times function sphere are the same because it's just a 4 times function sphere. So let me try to draw it. Getting my conventions. Okay, if you stay on the right picture for a second, you actually see that it's topologically just the middle picture, or the wannabe middle picture, by just pulling those lines up and down. And of course, the same way, the other way around is the same. Okay, and that leads to the notion of a Frobenius algebra. So Frobenius algebra is just an algebra which has a completely topological diagrammatic description, meaning it's a co-algebra, an algebra and a co-algebra satisfying the Frobenius relations. Let me write an F. So it's F, and you have a multiplication, you have a unit, you have a co-multiplication, you have a co-unit. In some monoidal category C is an algebra and a co-algebra satisfying Frobenius. And the example, which I will put right here, is of course this guy is Frobenius algebra. Invalid. So what do I need to check? I won't do it because I'm doing bad on time. But what I need to check here would be that the co-multiplication is a co-unit, which I had on the previous slides. This one, for example, that they satisfy the Frobenius equation. So this one. This is the crucial. Okay. And what is the point of all of this nonsense? Let me summarize, or before I summarize, I'll give you some examples. Okay, so let's say you have a Frobenius algebra. And then I could define a cup as follows. Or in other pictures, I would define something like this, a banded. So here's again this line. A banded cylinder would be just, well, what would it be? Something like this. And I could define, of course, the other way around. No way why I should prefer bottom or top. So, definition. This guy, and of course course. And then these satisfy the following relations. Satisfy. I just draw you a few of them. Basically all topological relations you can imagine. I will make a precise statement in a second. But for instance, I could imagine that something like this should hold. Well, and indeed, if you stay on the picture, well, it was this one, whatever. If you stay on the pictures, it would look like this. And a pretty obvious relation. Oh. Again, let me draw the spline. Basically everything you can imagine, which shows topologically, like this one, maybe another one, like this one. In spline diagrams, it looks like this. Well, right, you take the diagram, you pull the string down, and it looks like this. And of course, it holds. Just let me do the other picture. Well, you just take this slack and you pull it down. And so forth, etc., etc., etc. It's all topological pictures you can imagine. Hold for those multiplication maps in those co-multiplication, those maps associated to a Frobenius algebra. In particular, you do not never ever need to check that anymore, right? I'll give you a huge example in a second. It just comes for free. You just use your topological intuition to deal with those diagrams. The big proposition you want to keep in mind, actually, it's a theorem. The book calls it a proposition. Call it a proposition as well. So this is whatever it is, 8.6 in the book. All planar diagrams, made from concatenations of those pictures. So whatever you can draw, represent equal morphisms if the corresponding spline diagrams or topological diagrams are isotopic. Planar isotopic. Let me call it planar isotopic. Cool. Right. In words, this is just saying anything you think will work works, and this is pretty good. Let me give you an example why this is so pretty good. Back to my Frobenius algebra Cx modulo x squared, and I have those maps. This one, and I've written it down explicitly in coordinates. And okay, let me do a calculation in coordinates. Let me calculate this diagram. I call this a handle. This is called the handle operator. Why is this called the handle operator? No, see? Because if you draw it like this, actually what's going on? It looks like that. So you're adding a genus to a diagram. Every time you do this, you're adding a genus to a diagram. And in coordinates, this is just the other way around. Multiplication first delta with multiplication. And what it does is the following. So it sends 1, 2, it sends x 2. Okay. Multiplication in this example sends 1, 2, 1 to x plus x to the 1. And this was x to x. And you send it a bit further. So this was delta, and that was mu. You just multiply them, but x squared is 0. You just multiply them. So we get 2x. Okay, so far so good. Let me do this one then. So the handle operator is this operator. So let me do the other operator, the twice handle operator. So it's spine diagrams. This is just well, if you look at the calculation, actually this is the map that sends 1, 2, 2x, and we already know that x goes to 0 under the second handle operator, so this goes to 0. And x goes to 0 anyway, so this is just a 0 map. Good. And why is this nice? Well, let me do one more calculation. Just this one. So this is a map that sends 1, 2, 1 tensor x plus x tensor 1. And then sends it further to 2x, to 0, sorry, to 0. Why? Because I would apply, so this is first iota then epsilon, and epsilon kills all those products because epsilon kills this guy. Okay, and in terms of topological diagrams, this is just a sphere. Very good. So let me go up. So what I've just done now is I've analyzed my example a little bit further, and I realized that, okay, the handle operator does something. The twice handle operator is already 0. Of course, then 3 times handle operator is also 0. And the sphere is also 0. In particular, if I would draw now, here you go. Some morphism. And I really will draw A now. So whatever I want. Let me see. Here's one. Is this a legal morphism? First question. Yes, because I can always height move it. I won't do it. Because of my proposition, I can always height move it, such that it's really built out of basic pieces. You can see basic pieces like here, for instance. Here's a basic piece. You have cups, you have height points, and so on. Well, basic pieces. And you wonder actually what kind of morphism this thing is. And there's one way to do it. Well, you can now do height moves and do exactly the same coordinate calculations like I did above. Or you could use the following topological trick. So this guy is just topologically equivalent if I would draw it in terms of those diagrams. I have 4 legs on the bottom. So here's my bottom. I have 3 legs on the top. Very good. You can always arrange everything such that I have this. And then a certain number of handles in the middle. So G handles. So what I have to do now is I just need to count the handles on this side. So here's one, 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 here's one. So the genius of this thing is, one, two, three, four, five, six, seven, eight. In particular, you already know that the morphism is 0 because, well, the handle operator applied more than once is 0. And I had to do no work at all. I just counted the geniuses. And an exercise would be now to do the same in coordinates, and this is just tiresome. Whatever. So those topological arguments are really, really powerful. They really save you a lot of time. We have seen this last time already, but here's another example. It is just ridiculous how efficient the diagrammatic notation actually is. Instead of computing here whatever it is, a huge morphism, I just say, okay, I know a handle operator is, a twice the handle operator is 0, I just count the genius and I'm done. It's just so more efficient than doing it by hand or in coordinates. If you want to think about it like this is, well, a smart way of doing linear algebra would be to do it coordinate free, so basis free, and this kind of a basis free variant of doing something like categorical algebra or some kind of algebra. Okay, so diagrammatics is really powerful, and a nice instance of diagrammatics where it's really, really powerful should be our Soergel bimodules. So how do we make now connections to Soergel bimodules? And in order to make connections to Soergel bimodules, actually I want to ask the question, how to produce actually Frobenius algebras. Right? Whenever you have a Frobenius algebra, you know topology works. And this is actually the title of the lecture, using Frobenius extensions. So a Frobenius extension, so this is the question, the answer will be, well, such a vague question can't have a very well-defined answer, but some answer would be a Frobenius extension gives us Frobenius algebras. So a Frobenius extension is the following data. So all I need are two rings, A and B, two commutative rings. So anything you can imagine, any commutative ring, integers. Our ring R, I will give you an example in a second. Our ring R from Soergel bimodules will be one of those, and so on, or a field or whatever you want. An inclusion and I will call it I. So one of them is a big ring, the other one is a small ring. So you should think of as A being the ground field, you will see it on the ground ring, and B is kind of the thing you're interested in. And the only thing you additionally need is a linear map. So a linear map, which I will call delta. And this goes the other way around, from B to A, such that, well, a little bit more space. I want to put it on what page? So that, oops. Very good. Such that I will give you an example in a second. So it's actually pretty nice, but still I will give you an example in a second, which is very, very explicit. There exists a basis there exist bases, I'm sorry, not one basis, two. Of B as an A module, right? B is naturally an A module. Why is B an A module? Because you have this one. A acts on B. Let me give those bases names. This is again my Blackboard management, or whatever you want to call it, is not very good. The bases smaller. Let me give those guys names. I will call one BI, and I will call the other one BI star. And I is some index I, some finite index set. And they satisfy the following: the bases are dual. That's why my notation. They are dual. Meaning that delta of Bi Bj star is exactly what you think it is, like the Kronecker delta. It's 1 if I equals j. It's 0, well, if I is 1. Okay, that's all I want. I want two rings, and they're nicely connected by those two maps I and delta. Very good. And this guy is usually sometimes called a Frobenius trace. That's just the name. And the point is the following, which I will put underneath here. And I really call it a lemma because it's not very hard to check. So if you have that, then you actually have 4 A bimodule maps, even stronger, not just linear maps, but A bimodule maps. Everything, so A is, as I said, like the round field, so it should be, everything should be relatively linear with respect to A. And there is I from A to B. There is delta from B to A. And you have this one. There's an M from, or yeah. So B, using the inclusion, is naturally an A bimodule, and I can tend to it already. And you have a map from here to here. I'll give you an explicit example, as I said, in a second. And you have the opposite. And the point is, here's my lemma. Okay, you have 4 maps making B a Frobenius object. This was supposed to be object in A bimodules. Or A bin, whatever. And those maps are actually given completely explicitly. Okay, here comes the main example I want to keep you in mind. Yeah, examples. So kind of the naive case is if A is a field, K and F is a Frobenius, B is Frobenius algebra, then you recover the usual notion. this is a Frobenius extension. No, this gives a Frobenius extension. Okay, now I want to do the following. Where am I? Ah, here am I. Very good. So take A to be our R. Remember that was just this the polynomial ring in the alpha S's. And I want to take B to be S, which was just very good. And what are our structure maps? Structure maps are as follows. This one is easy. Oh, sorry, I'm ahead of myself. This is my second example. Let me move it to the bottom. There's actually a nicer one, or an easier one. I take B to be R and A to be RS. So symmetric polynomials, this was S symmetric polynomials. Okay, and then there's an inclusion. What could it be? Well, any symmetric polynomial is obviously a polynomial, so you can just include it. This is just the inclusion. We have a delta map the other way around, and we have seen this delta map actually. This was our Debazu operator. I will need you in a second. I don't know. Okay, and then the lemma tells us that there are two other maps, M, and the map should go from R, RS, R to R, and the delta should go from R to R, then RS, R. And the maps are pretty easy. The multiplication is just the multiplication. Of course, here elements are tensors of polynomials, and some of them slide to the other side if they are symmetric, but in principle, they're just tensors of polynomials, so you can just multiply polynomials together. And this one is nice. And you might wonder at one point, where on earth do I need those dual bases? This one in coordinates is always the following. It's always the sum over the dual basis elements. A non-trivial check would be that this is actually independent of the choice of the dual basis, but it is. But as a reminder, for instance, in this example of Cx mod x squared, you actually have seen something like this. And yes, x and 1 are dual, are exactly the dual basis of so bi. The bi's would be 1 and x, and the bi duals would be the other way around, x and 1. This is extremely explicit. Whenever you have something like that, you get those maps. And in this case, we have seen this before. This was, I think, the element C, or whatever it was called. I will write it down again. It's this one. Very good. Very good. Okay, let me summarize this example. Here's another instance of a Frobenius extension where symmetric polynomials are a round ring, and the polynomial ring itself appears. And if you stare on this for a second here, this is actually nothing else than BS itself. Right? So what this actually gives us are two natural maps from R to BS, which I will draw as follows. And you will see in a second why I want to draw this like this. This is already a good hint that BS actually is very Frobenius. And yes, it is. Here comes the precise statement. Now I take B to be BS. So here we go. Sorry, B to be BS and A to be R. Very good. This is also Frobenius extension. Voila. You have this map. You have a delta map, which was the delta map from above. Very good. Which is a little bit confusing is here that this delta map is actually the multiplication from above, but it's a very harmless map. And you have two other maps, which I call mu, goes for BS, tensor over R, over A, right? But A is R, to BS. I will write it down in coordinates in a second, and there's a delta map from BS I will write it down in coordinates in a second, such that and here's my notation for them. This was a map, this one from above, and this is a map, this one from above. This is a map, this multiplication, this is a map like this, such that BS is actually in R bin. That's the whole point. And in particular, it's a Frobenius object in S bin. In Soergel. There was BS bin, that was versus Bott-Samuelson's, and there was S bin versus Soergel. And before I write them down in coordinates, note that this is really amazing because this already basically tells you what kind of relations you should expect in this horribly complicated, a priori horribly complicated category of Soergel bimodules. Namely, the objects BS are satisfy topological relations, right? The morphisms on BS. Topological relations. Yes. For completeness, I write down all the maps and coordinates, but you really don't need to remember them. The point, well, you need to remember them for my next example, and then you should forget them. Because I'm aiming to write down now a complete description of the category generated by BS, which is one color. Calculus, but S is my one color. And for that, I just need to write them down in coordinates. It's not so bad. It looks like this. So F tensor G tensor H actually goes to, and here you have an F tensor G goes to. I will comment on that in a second. So what I'm using here is the following little trick. So whenever I have a B tensor A, and we consider that in the category of B bimodules. So you have two copies, let me just bracket them. Oops. What you actually can do is, well, you cross off those guys and you get a map to B, tensor A, B, tensor A, B. So also it looks like you have 4 factors, you secretly only have 2. And now you can do, you can go to B, tensor A, tensor A, B, by using delta. This is again completely general for Frobenius extensions. And then you can go further by crossing out A and you go to B, tensor A, B. And this is exactly the step. And the other way around is, well, there's also the other way around, of course, which is applying I here. And those are those two maps, and the coordinates you just look like this. You don't really need to remember them anyway. The coordinates. Right. The point is, they're not making those up. They follow from being a Frobenius extension. Okay, we're almost done. So, question is now that I want to answer. So, what is now the one color calculus? Well, we know already the following. So one color calculus means if the category is spanned by R and BS, then I want to analyze those, and I know that I have maps delta like those maps, and I immediately know from Frobenius theory, from topology, that I have relations which look like this. Right, I should be careful here, I should label everything with S, but since it's just one color, I just omit the label anyway. So everything here should be labeled with S, like before when I omitted the color for the algebra itself. With this relation, the unitality, which I'm drawing a little bit sloppy. Anyway, you have, of course, the opposite relations. And again, I could draw them in terms of topological diagrams. I'm just drawing the spines. You have the Frobenius relation. Maybe I put it here. Which I can just draw like this. Why can I do that? Because this picture unambiguously means either this one, the other way around. Sorry, the other way around. But the relations force them to be the same, so I can just define this diagram here, this one, by just being this guy tossed to the side. Okay, that's for sure. That's the kind of relation that we have. And you only need a little bit more. That's almost it. And 2 extra relations. And before I write them down, let me remind you that the first relations imply that whatever kind of diagram I draw in those BS, in this category generated by BS, I can use topological intuition to manipulate it. 2 extra relations, and I want something for the Hegel operator, the Hegel relation. In this case, the Hegel relation is extremely strong. The Hegel relation was this one. Remember that was just, and this is actually the 0 map. So Soergel diagrams do not see any genius. if you want. And you got the other relation and the slight relation. And so you always, for any Frobenius algebra, you have some relations involving the genus if it's finite dimensional. And this is just a very, very strong condition here. So this is kind of, it doesn't really come from the Frobenius structure. It depends on your Frobenius algebra, on your Frobenius extension. But this is still kind of part of the Frobenius structure. And only the last one is really special. And that comes from the fact that we had those polynomial rings. And this is called the slight relation. And it looks like this. That's the only thing that is hard to remember, because there's a sign somewhere and I never get it correct. Probably something like that. So whenever you have this floating thing here, so this guy, and you want to pull it to the other side, that's like pulling a polynomial across the tensor factor. So it should only slide if it's symmetric. So you should expect an error term. And the error term looks exactly like this. Up to that, those guys are up to a sign, which I don't never remember. So this is kind of a Soergel relation. This is really an honest Soergel relation. This comes from our setup. The rest comes just basically from the fact that BS is a Frobenius object. Okay, and now I can play the same game. Of course, I could write now any crazy Soergel diagram I want. Anything I want. Here I go. Whatever it is. Here I go. And what kind of morphism is this? Well, I would count. Oh, this certainly overshots. So this would be 0, because in this case, the handle operator. Right, I can manipulate this diagram until it looks nice. That's what I mean by because of Frobenius. And on my handle operator is actually 0. And I had to do absolutely nothing. You now try to imagine yourself you're doing this computation in terms of morphisms of those BS bimodules. This is a non-trivial calculation. Oops. Very good. So let me wrap up. Yes, here's what we learned today in formal theorem. There exists, oops, f from, well, or where, oops, sorry. Let me give this guy a name. I get a category, a tensor category that I call HBS of type A1. So type A1 just means one color. This was this Coxeter diagram. Can't spell diagram anymore. Too many diagrams. Diagram. Very good. This is a monoidal category, and I just call it HBS for simplicity. This is a monoidal category, HBS. Has a monoidal unit, which is a ground ring. It has a tensor product, which is a tensor product over the ground ring, over our ground ring, and it's generated by BS as an object, or if you want just a, which you can identify if you want, which is just a line. So this should be a line labeled S if you want. So you can put lines labeled S everywhere, and so as objects, And morphisms are, of course, those guys. Morphisms. And this just means I can stack them together any way I want, subject to the above relations. So the above relations are the defining relations of my category. And this guy is called the one color Soergel calculus. Okay, and now, so HBS is a very, very nice, not a really, really harmless category. It's easy to define, you can use a topological intuition and everything. And what you get now is actually a functor from this HBS to SBIM, or let's say first to BSBIM. And of course, let me do this type A1 again. Such that F is well, it should preserve model. F is essentially surjective. That just means it's basically the equivalence on objects, so bijection objects up to equivalence, and F is fully faithful. Which means F is an equivalence and thus our category HBS is a diagrammatic model. Of BSBIM. And if you remember how SBIM was defined, then it's also a diagrammatic model. SBIM was just, so the way to go from here to here was just taking direct sums and direct sums and direct sums. And the second funny symbol is my symbol for direct sums. To summarize, here's the theorem. This funny diagram calculus, where you can really use your topological intuition to do anything you want, is equivalent to the algebraically defined category of Soergel bimodules, basically, if you want. Try to imagine doing, for instance, this calculation in Soergel bimodules. I don't say that's hopeless, but I think it's, well, it isn't hopeless, but it's way more involved than just looking and counting number of holes. Okay, that's it. Thank you very much for listening. Let me stop the recording.